The next speaker is Stan Ulam, who is one of the Los Alamos Aborigines. He is currently at Boulder. He needs no further introduction. The subject of his talk is von Neumann, the interaction of mathematics and computing. Stan.
Thank you very much. It's a nice introduction. I intend to talk very informally, and I suppose somebody said, I think our director or the chairman, that some people couldn't come because of age. I think I was invited because of age to give the speech. Indeed, I remember, before the war, before World War II, conversations with some of the great originators of the development of computing regarding the philosophy which led in a very short time to the development of electronic computing machines. It's very interesting that prehistory of computing is, say, covered beginning in 1937 by the next speaker, Professor Berkhoff. This very short span of time, 40 years, now merits a history. And in fact, our first talk was about historiography. This, of course, shows how accelerated the development of ideas and technology is now. There was, I am told by Garrett Berkhoff, already a precedent. There were meetings about the history of nuclear energy some years ago. Now this seems very funny because when you talk about histories and age, I thought people would ask me about my conversations with Pascal or with Babbage, but all I can tell you is, well, primarily about von Neumann. Well, I remember it must have been 1938 when we had conversations about problems in physics, mathematical physics. You see, the title is von Neumann and Mathematics and Computing, but it's very hard to separate, it seems to me, sharply, mathematics from the ideas of physics in this connection, or astronomy for that matter, astrophysics. And I'll go even further. Later on, I might mention, or call it music of the future, the possibilities, very great possibilities, which the same set of ideas and the same set of technological developments will have the consequences in natural sciences, in biology, for example, primarily, very soon. Now that, I think, is something that should not be neglected, even though this meeting is devoted to mainly to history. Now, I would like also, if that is all right with the organizers, to have questions asked during my talk. Because, you see, after an hour, or I won't talk that much, don't be alarmed, for 50 minutes, after that time, memory fails. Something comes to my mind. There is a very nice story, somewhat risque, but it was told me by Nick Metropolis first, and after the lecture, those of you who want to could ask him about the story, where the punchline is, memory goes first. Now, is that all right? Is it possible to have these little sticks with machines distributed during the talk itself, in case I make a pause and questions could be asked? Now, the first discussions, which I remember on this topic, were when Johnny von Neumann was very curious about the problem of turbulence in hydrodynamics. I think he had discussions with Norbert Wiener shortly before on this problem, and he was fascinated by the role of the Reynolds number, which, as most of you know, is a pure number of the order of about 2,000. It's a pure number because it's a ratio of two forces, the inertial and viscous forces, with the following importance. When the flow of a fluid is such that it surpasses, this number surpasses some value, let's say 2,000, the regular or laminar flow, as it's called, becomes highly irregular, turbulent. And both Norbert Wiener, in a sort of very general way, and von Neumann, who I think probably knew more practical physics than Wiener, wanted to have an explanation, or at least a method, of trying to find a way to solve this very puzzling, very large numbers. You see, small numbers like pi, e, and so on are, of course, very frequent in physics, or combinations of such, but here is a number of the order of thousands, and yet pure number, no dimension to it, whetting the curiosity. And I remember that during the discussions, von Neumann realized that the analytical methods, the methods of mathematical analysis, even the more sophisticated ones, were not powerful enough to give any hope for solutions in closed form. So I think this was one of the origin of at least his curiosity in trying to devise methods of very fast computations, so to say humble to the mathematicians at that time, and perhaps to some even now, ways of proceeding by brute force. Now that's what I think I remember we discussed on several occasions. And shortly after, I remember the discussions about the possibility of calculating the weather or meteorological phenomena, circulation around the globe. There was some marvelous analytical work from previous century, Laplace and so on, but of course not detailed enough to enable one to predict the motions of the air locally or not on anything but the very largest scale around the globe. Now, in this connection, I would like to point out again that some progress, of course, has been made, but not nearly as much as in the other fields which I'll discuss. I think Dr. Agnew mentioned some calculations which Frank Harlow here, his group, made about hydrodynamical phenomena. They are, so to say, in a sense, brute force approaches, and I don't know about the exact example which he mentioned, the motion of the air from California, where you put radioactive methane, but it must be, if Dr. Harlow is here in the audience, I believe the same sort of thing. Now, I mentioned the two cases where the progress in the intervening almost 40 years has been much smaller than in the other fields of mathematical physics, where the computers played a decisive role, as you know. It suffices to mention the study of the equilibrium, or even evolution or history of a star, the calculations without which it would be impossible to predict the behavior of star clusters or gases, etc. In many ways, what the original impulse was not what was immediately followed with rapid success. I think this is typical of developments in technology, that the original application of a new fact or a new tool is not what ultimately turns out to be the greatest success. In this connection, it occurs to me now, I remember when the nuclear energy was, well, call it discovered or made available, Chicago and here in Los Alamos, with the terrifying consequences. Again, it was von Neumann who remarked that the first applications of naphtha or gasoline, as we know it, was as a laxative. And look what happened in centuries to follow. That was, of course, to indicate that nuclear energy will have more interesting or certainly more beneficial effects and applications than the original one, which was bombs. Now, if there are any questions about these first years of discussion between some people, of course, the computing machines, not electronic ones, but say with the cogs and wheels, relay machines, were already being constructed, say at Harvard. You'll hear about it, I suppose, from Professor Berkhoff. He mentions 1937 in his title. And my remarks so far refer to 1938 and 9. Yes, Professor Hartwell.
Stan, the first time John ever talked to me about weather forecasting, my name is Cuthbert Hurd. The first time John ever talked to me about weather forecasting, he mentioned the name of Dr. Rossby. Did you have any interaction there, which you want to talk about?
Directly, no. I never met Dr. Rossby. Of course, there was a Swedish school of theoretical meteorologists, and some of the ambitions to calculate weather were, I think, I wouldn't say originating, but certainly developed by the Swedish group. And I think people from the University of California at La Jolla might know more about details of that. But coming back to this thing, I was not present at the previous talks between Norbert Wiener and Johnny von Neumann. He just told me about them. And a little later on, they apparently had a different point of view. Norbert Wiener thought that the computers, if you could use this word at the time, would be more analogy machines than digital ones. Whereas John von Neumann maintained the opposite view. Norbert Wiener said, well, it's a, so to say, hormonal activity of the human brain. More, obviously, there is no mechanical relay system in our brain. So he thought that the big development will go in the direction of some kind of systems of fluids, as he imagined it. Whereas von Neumann, right away, was thinking of applying the digital or binary or purely discrete systems. For one reason, I think, as many of you probably know, the first papers that he wrote, 15 years before, I think in 1924 or 5, were or even before his first publications, were in mathematical logic and in the study of formal systems. And again, it seems quite, to me, it's quite obvious and perhaps a matter of chance, fortuitous things, that computer development became possible by confluence of two entirely different sources, or at least two more. But one, the purely theoretical study of formal systems, how to express a description of natural phenomena, or even of mathematical phenomena, of course, themselves, by, as I think our previous speaker, Dr. May, said very, I think, felicitously, genetic development from, well, we call it axioms and rules of procedures. So the whole idea of proceeding by given rules from a given set, mathematically, at least, was studied, as you know, for a long time, and von Neumann worked in this field very, very successfully. And on the other hand, of course, the technology, the development of electronics came just in time And another thing, one hates to say it, but the war, the needs of the war accelerated probably the availability of money and the efforts, and accelerated the work, which, however, in this connection, I'll go to Los Alamos situation a little later, came several years later. Now, remember that he was, for many years, a very pure mathematician. It was only just before the Second World War that von Neumann became, to my knowledge, interested in not even only applications, strictly speaking, to mathematical physics or to technology, but to more concrete physical problems. His book on quantum theory, Foundations of Quantum Theory, is very, very theoretical and is, so to say, the grammar of the subject. It is an extremely valuable, important work, but it did not, I think, contribute directly to any truly physical new insight or, say, new experiments. There are probably some physicists here who might dispute that point of view, but in the large it is so. It's extremely important, as I say, about putting, tentatively at least, rigorous foundations to a new part of physics. But it was just before the World War. Maybe he, by the way, expected some kind of world catastrophe, and he thought that there will be a great conflict. Living here in the United States and having come from Europe, he was in a good position to see further. People who remained in Europe or who lived here probably could not feel these currents as well as he did. Now, well, my own involvement with problems of more practical, physical nature started when I came to Los Alamos. And let me just tell you that I arrived, I think it was the end of 1943, the last few days of 43, that I knew right away what the project was working on. And I was introduced to some physicists. I came into one of the rooms, and there was, to my surprise, von Neumann, who came on visits here frequently for periods, say, of a week or two. There was Teller and some others, and the blackboard was filled with equations, which you could see in other forms, in other equations, very complicated looking in other people's offices, which sort of scared me out of my wits. Because looking at all this, I said, never will I be able to contribute even an epsilon to any of that. Well, the next day and days after, I visited some of these offices, and to my relief, I saw that the same equation stayed still on the blackboard. It wasn't that somebody really developed or worked out something. Well, this staying on for a period of a few weeks, I began to feel better and said, one doesn't have to immediately produce any solutions. And, of course, right away, not that I was an applied mathematician, I knew a little physics in a sort of Platonic way, having always been interested in quantum theory and ideas of relativity and so on. But as I say, it was Platonic. It's an entirely different thing to have something more concrete to deal with. But little as I really knew about differential equations, partial differential equations or integral equations, I could see that there is no hope of any solution in a form by analytical work which would yield practical answers to problems which appeared here. Now, one of the first problems, which was crucial to the success of the whole problem, was implosion, behavior of the implosion of a spherical system. This word itself was highly classified during the war. It would have been a terrible breach of security to even utter it, and that was true even for a couple of years after the war, but as every one of you know, it became a secret of the how does one say it? Polychinelle, how do you say it in English? Everybody knows at least the word and what it involves. The idea was to compress a mass of material into higher density by surrounding it by explosive and trying to figure out what pressures, what densities will be possible, and how the material will, so to say, get to this configuration. And it was not enough to know the answers within a factor 2 or 3, but obviously one had to have a more precise numerical guess or estimate, let's say, of the pressure, let's say within 10% or something like that, which was impossible really to guess, or even to try to divine from some old analysis, theoretical work type reasonings. And I remember, here I must say, I had a long discussion with John von Neumann about using a completely brute force approach. He, being of course a great erudite in many fields of mathematics, in addition to his own, tried to work out, together with some of his collaborators, analytical methods, at least part way, to see what will happen if this material is pushed together. It was very unsatisfactory, and I was always sort of pressing him to try, well, step-by-step numerical procedure, assuming, of course, equations of state and so on, which were somewhat known with some accuracy, not, of course, precisely, and trying to get numerical work done. And von Neumann was also a consultant to the Aberdeen Ballistic Laboratory, so he knew that there are some computing machines. I have not read the article mentioned by Dr. Agnew, which Feynman wrote in a recent issue of, what is it, Engineering Review of Caltech, but where he describes the first numerical work involving a group of people here in Los Alamos and the unwieldy Friedens and Martians, which you remember were large objects, heavy things costing at that time several $100, perhaps you remember $400 or $500 each, which are completely, of course, eclipsed by modern little computers which can do 1,000 times more, many times faster, and cost, say, $35 or less. So this gives you, on one little sector, tiny little angle of technology, the idea of changes which came about. It's very amusing, by the way. I don't know whether Feynman in his article writes it himself, that Feynman listened to the sound of these machines. Later on, there was a machine 604, what was it called? 600, yes. And he could tell, he said, from the sound, how the implosion is going, which of course is apocryphal a little bit. But it is true that he could open safes where, whose owners forgot the combination. That is true, because I've seen him do it. He could listen to the tumbler somehow, and often, so this was the practical engineering method. The theoretical method was when he tried to guess whether the combination would be a secret combination would be a simple relation between numbers like pi, e, or h. Sometimes he would guess what the owner would try to have as his secret number to open the safe. That is actually true in one case at least. So I'm telling you that as a humorous example of the difference between theoretical and pragmatic way of proceeding. Now, so the implosion was one of the problem of implosion, I think, was one of the great impulses for developing fast computers. And people knew, of course, about the work which was being, well, it was in progress in Philadelphia. and von Neumann knew about it. And there was immediate support here during these months for getting all possible means to be able to calculate more exactly. Well, I mentioned the problem of implosion because it's easier to explain, but there were several other problems of this sort. The one I mentioned of equations of state itself required calculations. And that was, I think, the great contribution, well, not consciously or directly, but I think fundamental contribution that this laboratory made to this whole business, which is now, what, many billions, what, $50 billion a year? And if you think that, say, 40 years ago, certainly, or 35 years ago, the thing was zero, you see, you can only marvel at how nobody would have predicted it, of course, not even von Neumann, not anybody else, how all, well, not all embracing, but how enormously wide the applications of the fast computing machines will be. And I was talking of a few examples in mathematical physics. Now, in mathematics itself, which I think my title involves, things were much more slower. It was more of a luxury, since time was expensive on machines. It was more of a luxury to try to compute things of purely mathematical interest. They were, at first, in the nature of fillers, just like in newspapers, you know, there's a vacant space. On a computer, there was a vacant time. One could amuse oneself by trying to work on problems in pure mathematics, and the natural examples or the natural material to play with in those days was, of course, combinatorial analysis and some questions in number theory. Now, the computers, as far as number theory goes, have an older history. In fact, I was a student in Poland in the late in the beginning 30s, I think, 1929 or 1930, when I first heard from my professor Steinhaus that there was a mathematician in California who devised a mechanical way to find primes and study some of their properties by a system of cylinders with holes in them. And this mathematician, I remember the name as was given to me, was Lehmer. That was the father, and I think his son worked with it too. Professor Lehmer worked on these machines which facilitated the study of primes. But of course, when it comes to trying to get operations with primes or other questions of number theory and go to very large numbers and a very great number, it became possible only through the fast machines. Of course, through the electronic machines, made it possible for mathematicians, as I say, to play such games. Now, I say play because I would like to tell you about my own impression of where the whole field stands. It seems to me that enormous progress, which we see now, large as it is, interesting as it is still merely at the beginning of the story. I feel that the future holds even much more. As all of you know, the present machines execute instructions given in advance, essentially only that. And as far as the logical operations go, or arithmetical operations, as far as they are concerned, they are limited to Boolean algebra operations, to Aristotelian logic, and to the four arithmetic operations, and of course, the ensuing evaluations of integrals, derivatives, etc., etc. There is no doubt that a more abstract, more general way of studying and following the development of mathematical symbols will be possible, to not completely, but to the large extent, by new machines and I would like to say, since this is one of the first days, the first morning of the meeting, to just, so to say, make propaganda, if that is needed, for the work which would be parallel on many channels at once. Up to this time, essentially, still machines follow the course of one deduction after another, of one step, with, of course, reservations and caveats. But undoubtedly, in the future, perhaps near future, even, there will be machines more closely imitating certain features of our brain or of the nervous system. Now, that is another story. And before I come to that, to the possibilities which again von Neumann was very much interested in, namely the development, or the analogies first, between the working of computers as they were known at that time, and of the brain and the nervous system as it was known at that time. I'll mention some, well, very briefly, ideas and exchanges of thoughts a little later on, but perhaps I should stop if there is any question about what I said already.
Randall, Newcastle upon Tyne.
Sorry?
Randall,
Yes,
Newcastle upon Tyne. One of the things that I have attempted to prove or disprove is the story or legend of wartime meetings between von Neumann and Turing. They certainly knew each other well before the war. And just recently, I was told by Professor I.J. Good, who was working with Turing on cryptanalysis in Britain during the war, that Turing came back from a visit to the States in 1942 or 43, and without saying anything about where he'd been, amongst other things, posed a statistical problem to Good, who was his statistical assistant. And this was the problem of the likelihood of an explosion in one barrel of gunpowder spreading to other barrels of gunpowder set out on a grid. He mentioned nothing about atomic bombs or anything. And I was wondering whether you could throw any light at all on that.
Well, I know you mentioned Turing in your question before. I had a correspondence with Turing at the end of 1938 and in 39 about some questions which, so to say, vaguely have maybe something to do with computers. Namely, the idea was approximation schemata in group theory and in some continuous group, theory of continuous groups. And he solved one of my problems. That was just before the war came. And I think it was published, I've forgotten where, in some journal in this country. I knew that he had discussions with von Neumann before. I know nothing about his visit here. It is very hard to get any information about cryptanalysis or the work about deciphering and things like that. I know that von Neumann was involved in some such work. I could not get any information when I wrote to Washington, because perhaps, I don't know, some of it might be still secret. I had to have such information, I felt, because I was asked by American Mathematical Society officers to write an obituary of the life of von Neumann, which I did, which appeared so 1958, long time ago. And I wanted to mention, in a paragraph at least, this work, but I could not get any information about that. There might be some people who might know something about such things. I would say Gleason, perhaps, at Harvard. I think he might have been involved in work on combinatorics of ciphers and so on. So you could ask him if you are going to write something about Turing. And Andrew Gleason at Harvard University. Somebody? Yeah.
I am Julian Bigelow at the Institute for Advanced Study in Princeton. Can you hear me?
I don't see you, but... Oh, yes, okay.
It was my good fortune to work for both Norbert Wiener, or work with Norbert Wiener for 3 years from 1940 to 43, and with von Neumann from 1946 essentially until his death. I want to add confirmation to your description of the difference between the way these two men thought, both about computing machines and in general. I worked with Wiener in the area of computing devices for military purposes, but we did explore and discuss many kinds of ramifications of this particular kind of thing. What you say about Wiener's predilection for continuous variable and analog type of equipment is absolutely true, with one exception, namely Wiener did contribute to some extent to the formulation of information theory with Claude Shannon, and of course this is a finite sort of a problem. I think it may be worthwhile mentioning that that Wiener had a horror of purely combinatorial problems. He knew a great deal of mathematics beyond any question and was very profound in many areas. I once asked him to explain to me something about Diophantine equations, and he would never say anything at all because he was horrified by them. Since then, I have thought about why this was true, and I think the answer is really relatively simple. Wiener had extremely bad vision. When Wiener attacked a mathematical problem, he wrote certain things on the blackboard, most of which were not correct and many of which were not decipherable. These were merely sort of footnotes to his thinking process as he went along. Wiener thought entirely in terms of sort of function theory and models which he contained in his head. He did his research in his head, and the business of documenting what he was thinking about was a purely ancillary function to what
he
his
was a
process
wonderful
was.
but very childish person.
Exactly so. On the other hand, von Neumann, when he was working on a problem, would, besides doing a great deal in his head, would write down upon a blackboard or elsewhere precisely what he was thinking about at each moment, and if one took down and examined what he was doing, the center thought was always captured in what he wrote down. And von Neumann, therefore, was not handicapped in this way, and he could operate over a wider set of mathematical problems.
Now, any more questions, by the way?
I would also like to comment that I was present in at least one discussion with von Neumann and Wiener about the problem of turbulence in Reynolds numbers.
So, yes, sir. Professor Burke.
Burkhoff, Harvard. I think there's so much has been said about Wiener. I would like to add two comments. First place as regards turbulence, his ideas were childish. He thought that he was sure, and he put it out with that prophetic type of, he put on the air of a prophet at times when he was making these deep pronouncements, that it was atomic in nature. And until we got to the atomic and molecular level, we wouldn't understand it, whereas anybody who knows what a Reynolds number is realizes that's absurd. The second thing is that, of course, Wiener was primarily an analyst through the best part of his career, but he did write about Boolean algebra in his graduate student days. He was very conversant with discrete mathematics, and I personally think it's fair to say that Wiener lost his self-discipline when he became famous about 1934. Up through the time he wrote his famous paper on generalized harmonic analysis, he documented his thinking very carefully. His papers will stand up to any kind of criticism as well as almost anybody's.
Well, I was talking about how the applications of computers in mathematics started almost playfully. But remember, the theory of probabilities, which now is so fundamental for many areas of theoretical physics, statistical mechanics, even in quantum theory itself, of course, pervades all kinds of physical theories, and beyond that, you all know, in more mundane applications of mathematics. This theory started, well, the same way, by consideration of some problems in games of chance by a few people. I say it because I think that large as impressive as the development now is of the computers which now exist, and of the speculations, which again von Neumann had so much to do with speculations about automata in general, their construction, their development. These still are at the stage, so I wouldn't say infantile, but at a very youthful or beginning stage, and enormous things will happen intellectually also in this direction. See, in mathematics itself, Professor Lehman no doubt will give you examples, not merely of numerical discoveries of very large primes, but of hints which the heuristic or observational work on computer gives to be able to generalize or to prove some more general facts. He'll talk about that. Now, among other things, the examples now are too numerous to mention. Let me tell you that of von Neumann's complete works, published posthumously, which have 6 volumes, the largest volume with the most pages, the volume 5, is exactly on computing, on automata, and on certain applications of computers to physical problems, and a few to little mathematical pastimes. These mathematical pastimes became important again as precursors of something much more useful in the near future. I won't have time to tell you about such combinatorial schemata as, for example, are discussed in Professor Burks's book on automata, cellular automata, which owes so much to von Neumann, or to things which, well, people played with, and of which Conway's game is perhaps a very well-known example. All these things are, so to say, practice in the same way that playing is for animals, for a future theory which will have more realistic or more true, if you want to say, use this word, interpretation in the living processes. And after the war, von Neumann again was interested in, starting with the analogies between the computer and some of the processes, mental processes which he employed. He was interested in the working of the brain. He published some articles on it. This is still, of course, as well, some Greek poet, I've forgotten which, who said that many are wonders, but the largest wonder of all is the human brain. Well, we are not yet at the stage where we can say something very meaningful about even the nature of human memory. Or, you see, there are controversies between physiologists of completely fundamental nature. Does it reside in molecules, or is it merely the system of currents between the neurons in the brain? Even that simple distinction or dichotomy is not at all resolved. Nobody has really any idea of how the memory works. But probably some partial understanding will come, and with it more studies of this parallel work, which is so superior to the ways even the best computers work now, and the search mechanisms, and the special language, which must be different, as already von Neumann realized, the language which the human brain employs, different from the ones we use in putting problems on the computer. The impressive thing from the beginning was the speed of the calculation. Some of the sort of objections or fears expressed by mathematicians about the use of computers were, oh, the numbers become so large, even for simple problems in combinatorial mathematics, that even the biggest computer can't begin to touch them enough to give us confidence of how they behave. But this is less and less true. I could cite you some amusing simple statements actually from the last few weeks of work, and not very great work, where situations involving billions and thousands of billions of possible alternatives could nevertheless be discussed or sieved through machines in a very short time of a few minutes. There's one problem I could tell you about, which I tried to study. Strange enough, one can do something on a computer. Is a sort of simple, mutilated version of the four-color problem. As a little amusement, and to digress from my main theme, I can tell you that about this old problem, which is the following. You have a map on a sphere or on a plane, a fictitious map, any one you like to draw, of countries, which you have to color in such a way that adjoining countries which have a boundary in common, should be colored by different colors. The conjecture is that you can always do it with four colors. Nobody managed to prove it. Now, people have tried successfully, using the computer, push the number of countries for which you can still assert that this is true up to, let's say, 70. I don't know what the record is. But here was another little variation of my own, which involves a little infinity. So it's not entirely finite problem. Imagine that you have a strip, a band of countries, each composed of an assembly, say, of unit squares. The line is infinite, but the width is finite. Say the width is only 3 unit squares thick. How about drawing countries only in this band? Is the conjecture true? It was proved by some student. But recently, in the last few weeks, using the computers, some a former student of mine who works in Colorado, Mr. Cavender, managed to prove this thing, four-color conjecture, for bands of width 7. And this is tremendous work. Millions of cases had to be discussed, but at least that much. It's not a full infinity, but a little bit of infinity. The reason I mention is that mathematicians who are perhaps tend to be a little snobbish are not satisfied with anything that is purely finite as much as if there is even an inkling of infinity. So in order to hook mathematicians, so to say, in some of my own modest or humble attempts to interest them in some problems of mathematical biology, I always try to formulate it in such a way that they have sense not only for a finite end, but for a true infinity. Now, all this is a sort of psychological, merely, stratagem, but it will cease to be so in the future when, as I said, some elements of true infinity will be, by use of so-called quantifiers, mirrored on operations on existing computers. I know, because when I discussed this with von Neumann, that was also his not only hope, but belief. I use the word quantifier. I don't think all of you know what that is. Now, the Boolean expression, Aristotelian expressions in logic, which are and, or, not, that the machines do well. But mathematicians love expressions like the one I'm now to utter. There exists an x, such and such. Now, this exists is a quantifier. And the other quantifier is, for all x, something is true. So there are just two quantifiers. It sounds very innocent, but they have different character from the purely Aristotelian operations. And these have not yet been somehow pictured, even by approximation, on a machine, except in the most sort of childish way. So this is one of the possibilities, in addition to this constantly improving way of surveying larger and larger number of cases, which ultimately give, perhaps by natural induction, insight into the true basis of, say, physical facts, or if you want, sociological things. Now, if there are a few more questions, I think there's still a few more minutes for questions left, or I could talk about these von Neumann discussions for a long, long time, but...
Hello. While we're talking about von Neumann, I thought it would be interesting to throw a light on another little facet of his. The only trouble is that my talk is hedged by I don't know yet how classified this is, so I'm going to be extremely vague, but it does throw an interesting light on Johnny von Neumann. What they were doing at Los Alamos, Stan has already mentioned the sacred word implosion. I mean, I should say 9/10 of the world now know implosion is sometimes used in bombs. However, what they were doing here in those early days wouldn't work. It involved more or less exploding round something and imploding it, and it just wouldn't work. Well, the reason it wouldn't work is because they were considering explosive as if it was something that burnt, whereas, of course, really, the phenomenon of explosive going off is a wave process. So when it became realized by one or two people that you really had to take account of this wave process, people, at least a person, started to think about optics and worked out sort of how you could possibly make points that started the explosive all converge onto one point. Well, when you do the mathematics of this, you emerge with fourth order surfaces between explosives and so on, and you pretty well had to fill the rest of the world with certain kinds of explosive in order to make it do this. Well, the equations were worked out, and it looked as if it was a lovely idea, but it was not practical. I remember Johnny listening to this talk and going away, and the next day coming out with an extremely snappy piece of geometry, which is not present in geometrical optics, in optical things, which solve the problem completely. It's a very nice piece of geometry which he saw overnight. So that was, and John von Neumann's contribution was really why the implosion worked, because of this snappy piece of geometry. I can't tell you what it's called.
Well, of course, he had many brilliant insight into many problems. This was just one of them. I think Dr. Howard has...
I have to hold it. Sorry. Arthur Burks, University of Michigan. I wanted to remark first that the idea that von Neumann used of a cellular automaton to develop his theory of self-reproducing automata came from a discussion he had with Stan Ulam, came from Stan. And I wanted to ask Stan a question about the antecedents of this. In your book, you tell of early thoughts you had on self-reproducing automata, at least from the point of view of states or structures or patterns back in Poland.
Yeah,
could you say a little more about that?
Well, this is just a reminiscence. In 1930, I would say in 1933 or 4, I and some other mathematicians, Mazur and Banach, who was an older professor, a very brilliant mathematician, had a discussion on the coffee house about ways to make some assembly, mechanical system, multiply if given enough food or material, raw material around it, and how to do it. You see, by the way, it was Mazur who invented the idea of infinite games, which only mathematicians can play. And that was just the beginning of the concept. This, by the way, the idea of self-reproduction of the automata, which von Neumann put so much store in, turns out not to be so very deep and not to be so essential or crucial it seems to me. Tragedy, I should now perhaps say that to you. In a way, it's like Moses who saw the promised land only from a distance. Von Neumann did not live to see the work of Watson and Crick on how the self-reproduction really works in an incredibly simple way. It's hard to guess. He did not live to see all the developments in physiology or anatomy in the brain, or the ubiquity of the little computers, or the whole improvement in speed, etc. What remains to be done. It's not so much, it seems to me, the study of developing reproduction itself, but differentiation, that is to say evolution, true evolution, which depends on sex or nonlinear phenomena, that's what it amounts to, and on the survival of the fittest in competition. You see, that's the next chapters of the theory of automata, which, of course, Professor Hurd could tell you much more about than I can.
Yes, he was concerned with those problems and did think about them, but you're right, he wasn't able to work on them.
Dick Lamer, University of California, Berkeley. Stan, you began with some comments about new machines and how they're going to be more parallel and so on. I want to remind you,
Thank you, sir.
That our first electronic computer was highly parallel, and it was John von Neumann who ruined it by making it a sequential machine.
Well, you mean in the sense that my 5 fingers are parallel, or was it much more than that? Well, our conscious, of course.
John Mockley will tell you all about that in due course.
Good. You see, our conscious reasoning on things we write down is linear, but our real search in memory and the process of thought certainly goes on very, very many channels. See, at von Neumann's time, I'll finish in 1 minute, don't worry. I remember in the discussions with von Neumann about the brain, the great marvel that there are many billions of neurons. And perhaps he told me, I didn't know that, he told me, between some of them, there are as many as 50 or 100 connections, in the center perhaps 1,000. Now, today, this number 50 or 100 is 5,000 or more, and in the central region, maybe 100,000. So the complications grow even in anatomy, not only in foundations of physics or in astrophysics. Everything becomes much more complicated than we thought of at first. Thank you.